So today I want to tell you about the multinomial distribution. This is a distribution that arises when an experiment has more than two possibilities. Maybe it has low, medium, or high, and we want to count the number of highs, the number of mediums, and the number of lows. As always, let's start with a story. Eagerly, the alchemist watched the 5 potions on the table. For each potion, there were 3 outcomes. There was a 10% chance the potion would hurt the drinker, a 20% chance that it would do nothing, and a 70% chance the potion would help the drinker. If n sub 1, n sub 2, and n sub 3 represented the number of hurt, nothing, and help potions respectively, what would the covariance matrix of these random variables be? In the Bernoulli process, each trial had only 2 outcomes, failure or success. What if more than 2 outcomes are allowed? Suppose that there are m different outcomes possible. In the story, there are 3 outcomes for the different types of potions. There were 5 potions being brewed. That means that 11231, 33212, and 33333 are all possible outcomes. Altogether, there are 3 to the 5th power different ways for the 5 potions to turn out. That can be simplified if, instead of caring about exactly which potion was which type, the only question of interest is how many of each type of potion was created. In that case, if there were 5 trials and the result was hurt, medium, help, hurt, represented numerically as 1, 1, 2, 3, 1, then the count of results would be the vector 3, 1, 1. This indicates that there were 3 type 1 potions, 1 type 2 potion, and 1 type 3 potion. Similarly, 3, 3, 2, 1, 2 gives the vector 1, 2, 2, and 3, 3, 3, 3, 3 gives 0, 0, 5, because there were no type 1, no type 2 potions, and 5 type 3 potions. Let n sub I denote the number of potions of type I created. Then, because there were 5 potions to start with, n sub 1 plus n sub 2 plus n sub 3 have to add up to 5. Moreover, n sub 1, n sub 2, and n sub 3 are all binomially distributed. In particular, n sub 1 is binomial with parameter 5 and 0.1 since there are 5 potions, aka trials, with a 10% chance of each trial coming out type 1, which is what's counting as a success here. For the type 2 and type 3 potions, n sub 2 is binomially distributed with parameter 5 and 0.2, and n3 is binomially distributed with parameter 5 and 0.7. So these random variables are not identically distributed. They are also not independent, since again, n sub 1 plus n sub 2 plus n sub 3 equals 5. So knowing n sub 1 and n sub 2 allows the calculation of n sub 3. So they cannot all be independent. The name given to the joint distribution of the n sub I is multinomial. Suppose for I running from 1 up to m, n sub I binomially distributed with parameter n and p sub I, and n sub 1 plus n sub 2 and so on up through n sub m have to equal n. Then we say that the vector n sub 1 up through n sub n has a multinomial distribution with parameters n, p sub 1, p sub 2, up through p sub n. And we write that this vector n sub 1 up through n sub n is multinomial with parameters n, p sub 1, up through p sub n. Recall that the set of n tuples, where each coordinate is in 1 up through m, can be written as the set 1 up through m raised to the nth power. So for instance, 1, 1, 3, 2 is an element of the set 1, 2, 3 raised to the 4th power. Then for trials w sub 1 up through w sub n, an element of 1 up through m to the nth power, the sum as I goes from 1 to n of the indicator that w sub I equals j counts the number of trials whose outcome was j. combine all of these sums together to define the f sub count function. So the f sub count function applied to a sequence of values, w sub 1 up through w sub n, is, as its first entry, the sum of the indicator that w sub j equals 1. The second entry would be the sum of the indicator wj equals 2, and so on up through the sum of the indicators that w sub j equals m. The next fact uses this notation to describe exactly what the multinomial random variables are counting. Suppose that w sub 1 up through w sub n are IID, where the probability that w sub j equals I equals p sub I for all j from 1 up through n and I from 1 up through m, and the probability of equaling 1 summed through the probability of equaling m equals 1. Then f sub count applied to our random experiment w sub 1 up through w sub n will have a multinomial distribution with parameters n and p sub 1 up through p sub n. The proof is verifying that each of the marginal distributions for the n sub I does have a binomial distribution. And because we're adding together all the experiments, all of those variables have to add up to n. And that shows that the resulting distribution is multinomial. Now, to understand the density of the multinomial distribution, first we need a bit of combinatorics. Consider sequences of length n consisting of the numbers 1 up through m. The number of sequences where each number I from 1 up through m appears exactly n sub I times is called the multinomial coefficient, and it is written in parentheses with an n on top and n sub 1 through n sub m on the bottom. In terms of the f sub count function, the multinomial coefficients count the number of inputs to the function that results in the count n sub 1 up through n sub n. That is, this multinomial coefficient, n choose n sub 1 through n sub m, is equal to the number of sequences of length n using elements of 1 up through m, such that f count applied to that sequence has n sub 1 1s, n sub 2 2s, and so on up through n sub m values m. It is the multinomial coefficient because of the following fact about multinomials. For m and n positive integers, if you take x sub 1 plus up through x sub m and raise it to the nth power, that's equal to the sum over all non-negative integers n sub 1 through n sub m that add to n of the multinomial coefficient n choose n sub 1 through n sub m times x sub 1 to the n sub 1, x sub 2 to the n sub 2, all the way up to x sub m to the n sub m power. This fact follows directly from the definition and the distributive law. For instance, if I take x sub 1 plus x sub 2 plus x sub 3 to the fourth, that is equal to x sub 1 plus x sub 2 plus x sub 3 multiplied by itself 4 times. To multiply this out, I have to choose one term from the first factor, one from the second, one from the third, one from the fourth, and finally one from the fifth. And this is exactly like our random variables w sub 1 up through w sub 4, where w sub I is either 1, 2, or 3 for all I. For instance, if the choice of terms from each factor was x sub 1 from the first, x sub 2 from the second, x sub 1 from the third, and x sub 2 from the fourth, then multiplying gives x sub 1 squared times x sub 2 squared. Because multiplication of the x sub I is commutative, the number of ways of getting x sub 1 squared through x sub 2 squared equals the number of ways of choosing the first term twice, the second term twice, and the third term 0 times from among the 4 products. Now use these coefficients to write down the density of multinomial random variables. For a vector n sub 1 through n sub m multinomial with parameters n, p sub 1 through p sub m, the density of n sub 1 through n sub m at little n sub 1 through little n sub m equals n choose n sub 1 up through n sub m times p1 to the n1, p2 to the n2, up through pm to the n sub m. That's because p sub 1 to the n sub 1 times p2 to the n sub 2 and so on is the probability of getting a particular outcome with n1 1s, n2 2s, up through n sub m m's. And then the n choose n sub 1 up through n sub m is the number of such sequences that result in those particular counts. So how are the multinomial coefficients actually calculated? We use the following formula. For n sub 1 up through n sub n, non-negative integers that sum to n choose n sub 1 through n sub m is n factorial divided by n sub 1 factorial, n sub 2 factorial, up through n sub m factorial. The proof is a bit tricky to write formally, so here just an informal derivation will be given. Think of the multinomial as an m-stage experiment. At the first stage, n sub 1 spots are chosen from the n available to have w sub j equal 1. So that can be done in n choose n1, which is n factorial over n sub 1 factorial times the quantity n minus n sub 1 factorial ways. At the second stage, choose n sub 2 spots from the remaining n minus n sub 1 spots. This can be done in n minus n1, choose n sub 2, which is n minus n sub 1 quantity factorial, divided by n sub 2 factorial times n minus n sub 1 minus n sub 2 factorial ways. The number of ways to choose in the first two stages of the experiment are then the product of the ways to choose in the first two stages. So n choose n sub 1 times n minus n sub 1 choose n sub 2. And when you simplify that expression, two of the factorials cancel to say that that equals n factorial divided by n sub 1 factorial and n sub 2 factorial and n minus n sub 1 minus n sub 2 quantity factorial. Then multiplying by n minus n sub 1 minus n sub 2 choose n sub 3 gives n factorial all over n sub 1 factorial times n sub 2 factorial times n sub 3 factorial times n minus n sub 1 minus n sub 2 minus n sub 3 factorial. And the pattern continues. Carrying this through to all the stages of the experiment gives, after cancellation, n factorial all over n sub 1 factorial through n sub m factorial times n minus n sub 1 minus and so on up to minus n sub m factorial. However, n minus n sub 1 minus n sub 2 and so on equals 0, and 0 factorial equals 1, so it disappears from the product, which completes the proof. Now, if n sub 1, n sub 2, and n sub 3 are multinomial with parameters 5, 0.1, 0.2, and 0.3, then what is the chance that n sub 1, n sub 2, and n sub 3 equals 0, 2, 3? Using our formula, this is 5 factorial over 0 factorial times 2 factorial times 3 factorial times 0.1 to the 0 times 0.2 to the 2 times 0.7 to the 3, or 0.1372. Now the mean of each component of the multinomial follows directly from its marginal distribution, which is binomial. Recall that the mean of a binomial is the product of the two parameters. So for n sub 1 up through n sub m, multinomial with parameters n and p sub 1 and p sub 2 up through p sub m, the mean of n sub 1 up through n sub m is n times p sub 1, n times p sub 2, and so on up through n times p sub m. A similar situation holds for variance. If I have n sub 1 up through n sub n multinomially distributed with parameters n, p1 up through p sub m, then for each I from 1 through m, the variance of n sub I is going to be n times p sub I times 1 minus p sub I. Now, covariance is a bit trickier, since the components of the multinomial are not independent. If x sub I is high, that leaves fewer spots to be taken by a different type j, so x sub j should be lower on average. How low is given by the following fact. For I not equal to j, the covariance between x sub I and x sub j is the negative of n times p sub I times p sub j. For the proof, recall that the covariance between x sub I and x sub j is the expected value of x sub I times x sub j minus the product, expected value of x sub I times expected value of x sub j. Now suppose that the value of x sub I is known. Suppose that we know that 7 of the values of the experiments equal I. Well, that gives n minus x sub I spots that could possibly contribute to x sub j. Moreover, because these spots are conditioned to not draw their experiment equal to I, there is only a p sub j over 1 minus p sub I chance that w sub k equals j. Now use the fundamental theorem of probability to say that the expected value of x sub I times x sub j is the expected value of the expected value of x sub I times x sub j conditioned on the value of x sub I. This interior x sub I is a constant, so it can be brought out of that inside expectation. The x sub I comes along for the ride, and the expected number of experiments that go to j, given how many experiments went to I, is going to be n minus x sub I times p sub j divided by 1 minus p sub I. Now this latter factor is just a constant, so we can bring it outside of the expectation. And what's left inside is n times x sub I minus x sub I squared. Now the expected value of n times x sub I, the n comes out, we get another npi, so we are left with n squared pi. Negative the expectation of the square of a random variable is negative the variance minus negative the expected value of x squared. But that is just npi, and the variance of x sub I is npi times 1 minus p sub I. When we take all of this inside the brackets and simplify, we end up with n squared pi times 1 minus pi minus npi times 1 minus pi. Well, fortunately, I've got a 1 minus pi in the denominator on the outside to cancel both these things. And then I can simply write that this is negative n p sub I p sub j plus n squared p sub I p sub j. Hence, the covariance of x sub I with x sub j is negative n p sub I p sub j plus n squared p sub I p sub j minus n squared p sub I p sub j, and the last two terms canceling allows us to finish the proof. So that's the story of the multinomial distribution. It counts when you have 2 or more possibilities for the outcome of an experiment, all the different counts for all the different possible outcomes. See you next time.